Your database. One machine. Today it's running just fine. Let me ask you something. The day your users grow 10 times, how does it die? Not with a bang. It slows to a crawl. First, one query gets slower and slower. Then even the writes start backing up. Today, I'm taking one database from zero, from a single box all the way to real load. Just 3 moves. Tuning, replication, sharding. I'll run every one of them live for you. And everyone has a price. Let me start with the cleanest picture I can give you. Scaling a single database always comes down to 3 things.
1. Make this one machine faster. Add an index. 2. Too many reads? Copy the data out. Primary and replica. 3. Writes can't keep up either? Cut the database apart. Sharding.
The order matters. Squeeze the single machine dry first, then talk about replication. And only if you really have to. Sharding comes last. Because sharding is the most painful of the 3. Remember this ladder. We'll take it apart one rung at a time. First, let's see how a single machine hits the wall. I built a users table, 200,000 rows, and I just look up one email.
How does the database find it? Row by row, top to bottom. That's a full table scan. In the query plan, it says it in capitals, scan. About 5.4 milliseconds each time.
5 milliseconds. Doesn't sound slow, right? But this is O of n. Double the data, and it's twice as slow. 100,000 people querying at once, and this one machine just melts on the spot. First move, the index. What people call SQL tuning. I changed nothing else. I just added an index on the email column.
Look at the query plan again. Scan is gone. Now it's search, using the index. 5.4 milliseconds drops to 0.02 of a millisecond.
So what actually happened in between? An index is a self-balancing tree, a B tree. Instead of scanning row by row, O of n, you follow the branches, O of log n. 200,000 rows, and one lookup is only about 20 hops. Take it further. Now I want to filter by city and sort by time. So I build a composite index, city and time together, both columns.
The neat part, even the sorting step disappears. The plan used to have a temp B tree for sorting. Now it's gone.
That's a covering index. Everything the query needs is right there in the index. No trip back to the table. But an index isn't free.
I compared writing 2,000 rows with indexes and without. With 2 indexes, writes are about 1.6 times slower.
Why? Every row you write, you have to update every single index tree. Remember this line. Reads and writes are a trade. With an index, you spend write speed to buy read speed. And let me be honest with you. This is an in-memory database, so that 3,000 times number is an extreme case. On real disk, it's nowhere near that dramatic. Don't treat the multiplier as the promise. Treat the mechanism as the promise. Scan turning into search, that part is real. You've squeezed the single machine dry, and it's still not enough. The problem has changed. Too many reads. Second move, primary-replica replication. One primary handles the writes, and behind it, a few replicas handle nothing but reads. The read load gets spread out. But there's a trap here, and almost everyone falls into it. Replication is asynchronous. Let me show you. A user changes their nickname and refreshes the page right after. That refresh sends the read request to a replica.
0 milliseconds. The primary already has it. But for tens of milliseconds after that, the replica still reads back empty. At 100 milliseconds, it finally catches up.
That 60 milliseconds in between is called the replication lag window. The user clearly made the change, refreshes, and it's gone. They think, did that even do anything? That's read your writes being broken. You spent consistency to buy that extra read throughput from the replicas. Now let's go one layer deeper. What if the primary goes down?
Under async replication, the writes you already told the client succeeded, but that hadn't replicated out yet. Gone. The replication lag window is also a data loss window.
And the moment the primary dies, the system can only read, not write. You have to quickly pick a replica, promote it to the new primary, and shift the traffic over. During that stretch, writes are stopped. Don't want to lose data? Then go semi-sync. Wait for at least one replica to confirm before you tell the client it succeeded. The price is slower writes. See? Another trade. Replication solved reads. But what if even the writes are too much for a single primary? Third move, and the most painful one. Sharding. Take one big table, split it by some key into n pieces, and spread them across n machines. How do you split it? The most obvious way. Hash the key, then take it modulo, the number of machines.
I tried it with 100,000 keys and 4 machines. Split beautifully even, 25,000 each.
Perfect, right? Hold on. Business is good, so you add a 5th machine.
Data moved, about 80%.
Of 100,000 keys, 80,000 have to move to a different machine. Why? The divisor goes from 4 to 5, and every modulo result gets scrambled. When that happens, every cache goes cold. The back-end database gets slammed in an instant, like an avalanche. That evenness was fake evenness. The moment you scale out, it shows its true colors. Let's try another way. Consistent hashing. Hash both the machines and the keys onto a ring, and each key walks clockwise to the nearest machine. Then scatter 150 virtual nodes per machine to even it out further.
Same 5th machine. Data moved about 17%. And almost all of what moves goes onto the new machine. The old machines barely shuffle anything between themselves.
80% versus 17%. That's about 4.6 times. That's why real, production sharding uses consistent hashing. As always, one question. How will AI move this piece? First, where it plugs in and what it can do.
Auto-recommend which index to build, analyze slow queries, and turn plain language straight into SQL.
So who does it replace?
It replaces the DBA's craft of staring at query plans and hunting down which index is missing, one by one. And the bar for writing SQL gets flattened too.
What changes? Index and partition strategy goes from the old hand's gut call to a model watching the load and making suggestions. Look at the second-order effect. The DBA's job moves up from hand-tuning in the weeds to setting policy, reviewing the AI's suggestions, and being the backstop when things break. But let me put this on the record. I'm not shilling for anyone. Consistency, shard keys, replication topology. These strong consistency decisions, AI can suggest, but it doesn't get to make the call. Pick the wrong shard key, and what you get is a full migration. That price is too high. AI can help you tune. What it can't do is carry the responsibility for consistency in your place. This isn't knocking it. This kind of work is supposed to have a human sign-off on it. To wrap up, let me flag a few real traps for you.
1. More indexes isn't better. Writes get slower and a low selectivity column. Like gender. Is an index you built for nothing. 2. Denormalization. When you read a lot and write a little, you deliberately store some redundancy to skip the join. Reads get faster, but now you maintain consistency yourself, so writes get heavier. 3. Federation. Split the databases by function, each minding its own, but cross-database joins are gone.
Sharding is the same. Pick a bad key, and all the hot traffic lands on one machine. You sharded, but it's as if you didn't. Every move trades one thing for another. Let's wrap up. Scaling a single database, there's only one order to follow. Squeeze the single machine, then replicate to handle reads, then shard to handle writes. Index trades writes for reads. Replication trades consistency for throughput. Sharding trades easy scaling for the cost of migration. There's no free scaling. Every step forward, you're paying tuition. The database is split now, but maybe the shape of the data should change too. The relational database was never the only answer. Next time, let's talk about the databases that don't speak in relations, and when it's their turn to step up.